Welcome back. It's lesson 5. We're almost done with week 2. How about that? It's Calc 1, Math 221 at SUNY Geneseo, and today we're going to look at how to calculate some limits by hand. Because we don't always have technology around, we don't always have tables at our disposal, we don't always have graphs at our disposal, and we may want to find some limits, and we're going to work through some algebra that helps us do that. There are 2 basic limits to know right off the bat. One is that the limit of the function x as x approaches a is in fact a, and the other is that as x approaches a, the limit of some constant function c is c. Both of these are self-evidently obvious. In the case on the left, you've got the function y equals x. And as x gets closer and closer to a, the y values get closer and closer to this number, which is the function at a, but this is the identity function. So if the x value is a, the y value is also a. So that is self-evidently obvious. And on the other case, c is a constant. C's are constants here before us. And so that's the function c. And as x gets closer and closer to a, no matter which way you come, from the left or from the right, all of the y values are close to c because all of the y values are c. It is these 2 basic ideas that push forward much of the rest of what we do. Once you have those 2 things together, we can put limits together in the following way. So we're going to suppose, just for argument's sake, that there's some function f of x, and as x approaches a, its limit is L, and there's some other function g of x, and the limit of g of x as x approaches a is some number m. And we're going to establish, I'm just going to say that these things are true. To establish them in a rigorous way requires Math 324 real analysis, but I think they are generally intuitive. If you add the 2 functions together and take the limit as x approaches a, well, you add all these y values to all these y values. So these y values are getting closer to L, and these y values are getting closer to m, and so you get L plus m. And similarly, if you subtract the 2 functions and take the limit as x approaches a, these y values are getting closer to L, these y values are getting closer to m, so the difference is getting closer to L minus m. And unsurprisingly, if you multiply the functions together and take the limit of f times g as x approaches a, that is unsurprisingly L times m. And if you take the limit as x approaches a of the quotient f of x over g of x, well, that's L over m, but only if m isn't 0. If m is 0, then this is not a number, and that is indeed a problem. But wait, there's more. The limit of some constant times f of x as x approaches a. Well, what happens with that? Well, these values are all getting closer and closer to L as x approaches a, and this is just a scalar multiple, so this is just the number that stretches the graph vertically, so L gets stretched by a factor of c. And if we take f of x and we raise it to a power, well, if you take the limit of that function to the nth power, that's the limit to the nth power for all positive integers n. Similarly, if you take an nth root, so the values of the function are getting closer and closer to L, we're taking nth roots of those numbers, so those numbers are getting closer to the nth root of L. This is true for odd n and for even n if L is greater than 0, greater than or equal to 0. If L is a negative number, you can't take an even root because we don't deal with complex numbers in this course, and there was much rejoicing. So why do I care? Like, why does all of this stuff matter? Well, let's pretend that I don't have my calculator handy and I'm looking to find the limit of x squared plus 3x plus 5 over x minus 2 as x approaches 3. If I'm trying to find the limit of this weird function as x approaches 3, and I don't have a calculator, I don't have an anything, and I'm wondering what am I going to do with this? Well, here's what we do. We think to ourselves, this is a quotient. So I should be able to just take the limit of the numerator, the limit of the denominator, and divide them. Well, that's great. So what's the numerator? Well, the numerator is a product and a product and a product. Well, that's a number, all added together. So I should be able to focus on this piece, figure out what that does, this piece, figure out what that does, this piece, figure out what that does, and add them up. Well, I know that the number 5 is going to stay 5. The limit of 5, no matter what x approaches, is 5. And I know that x, as x approaches 3, x gets closer and closer to 3, and that's just a scalar multiple. This is that c times L business. And then this is just a power. So that gets closer and closer to 3, and we just square it, and that's your numerator. And then we look at the denominator and we say, okay, well, what's happening down here? This is a difference of two functions. This function gets closer and closer to 2 because it is 2 all the time. And this function gets closer and closer to 3 because x gets closer and closer to 3. And so there it is. And we have 23. So you're asking yourself, wait a second, couldn't we have just plugged 3 in to start with? And the answer is yes. But the reason you can just plug 3 in and go is because all of these are true and all of these are true. So if those were not true, we would not be able to just plug 3 in and go. This extends for all sorts of polynomials, all sorts of rational functions. If you can substitute the number, great, do it. But that's not always the case. That's not always the case. And in our follow-up video, we'll take a look at what happens if that's not always the case.